Now I request Ojaji, please welcome our co-chair and chairman and start the session.
Thank you, Kapil. Very warm welcome and good morning to all of you. Actually, in this session, we have 9 presentations, and out of 9 presentations, the time allotted to each presentation is almost 10 minutes, and I would request chairman and co-chairman to evaluate each presentations based on which it is a feedback to us to decide which paper is the best paper out of the session. And with these remarks, the biodata of the chairman and co-chairman has been visible on the screen, so I am not reading it. So after this, I would request chairman to proceed with the session.
Okay. So good morning all. First of all, I would like to thank each and every delegate present here for this wonderful session. And I appreciate NCCBM for arranging such an innovative technical session. The topic for this session is net zero emissions, carbon capture, utilization and storage. It's in line with our net zero commitment, that is the need of hour. According to the World Resources Institute, out of total greenhouse gases, approximately 74% contributor is CO2. Considering CO2 as the max contributor, we need to concentrate more on the reduction of CO2 emissions. Yesterday we already discussed, cement industry alone is responsible for approximately 7% of global CO2 emissions. Hence, it's our joint responsibility to reduce the emissions and ensure self-living conditions for future generations to come. So, all are working jointly, researchers, equipment manufacturer, along with industry professionals to overcome the CO2 emission problems and achieving our targets. We need to accelerate our actions to achieve this target. In line with it, we have 9 presentations, as mentioned by Mr. Ojha, on this topic in this session. So these presentations are by industry researchers, industry experts, international level pioneers in equipment manufacturing and government agencies. They are going to present us their perspective, expert opinions and suggested roadmap to achieve the net zero targets. With this remark, I would like to invite our first presenter to start their presentation.
Thank you, sir. Thank you very much. This presentation, role of CCUS in decarbonizing Indian cement industry. So when we say cement industry, it's not only alone cement industry. The whole cement, concrete and construction industry should be viewed together. And cement industry is a subset of the whole value chain, cement, concrete and construction industry. Because only targeting in cement industry, we cannot achieve the net zero emission. We will see in the presentation this statement is correct, how it is correct. So, next slide. Okay. So, we all aware the Prime Minister Modi ji and its commitment during the COP21, Panchamrit, a net zero target for India by 2070, and installing non-fossil fuels electricity capacity of 500 gigawatt by 2030, sourcing 50% of energy requirement from renewable sources by 2030, and achieving carbon industry reduction by 45% over 2005. The sum of this target has been already achieved. And for limiting increase in global temperature of 1.5 degrees centigrade, requires achieving net zero carbon dioxide emission globally in the early 2050. And therefore, this 5 levers or 6 levers has been mentioned. The substantial reduction in fossil fuel use, widespread electrification, improved energy efficiency, use of alternate fuels, using materials more efficiently, reusing and recycling products, and minimizing waste. So we can see the status of CO2 emissions from the Indian cement industry. So globally, cement sector emits 7% of the total anthropogenic CO2, and CO2 emission factor is 1.12 in 1996 to 0.670 indirect emission per ton of CO2 per ton of cement in 2017. So we have achieved quite a lot. Cement industry is moving towards decarbonization, and cement industry should take forward the concrete industry together. So sources of CO2, we all know direct, which is from calcination in between 55 to 60%, and fuel combustion in between 30 to 35%, and indirect emission from electricity, which we are using during the manufacturing process. It's ranged in between 8 to 10%, and transportation, which is logistic, in between 2 to 5%. So with this, we can say the kg per ton of OPC out of these 3 components, total 835 kg per ton of cement. So 5 levers of decarbonization: substitution of clinker, alternate fuel and raw material, waste heat recovery, improving energy efficiency, and newer technology like renewable energy, novel cements, carbon capture and storage, and utilization. So all these 5 are from cement industry point of view. Out of 4 levers, all above, we have some scope still in alternate fuel and raw material. Some of them, like waste heat recovery, it is estimated in between 1400 megawatt to almost, and 900 megawatt perhaps we have achieved altogether. So the balance is known to us. Alternate fuel has a more scope out of this. And if we are not doing anything, then it will be a scenario of 6 degree rise in temperature, we can see, and it will lead to 0.62 ton per CO2 per ton of cement. But in 2017 itself, the Indian cement industry has achieved near about 0.58 ton CO2 per ton of cement because of the component of blended cement we have been using it, right? So by 2050, in 2 degree scenario, 0.35 ton CO2 per ton of cement we are targeting. And now the new target is 1.5 degrees scenario. So we have to achieve more. So what is the industry average is? We can see the major cement producers. It is in between near about, it is less than the 582 perhaps. So if we average it, taking all other cement manufacturers into consideration. So we have achieved a lot. So, but let us see what is the potential from everywhere. So, as per GCCA report, so 11% from clinker and other clinker substitution, 9%, and this 6%. So, if we all together, from cement, it's only 25% of the reduction potential is there. And if we combine together the concrete production and the design optimization and this 6% perhaps concrete, which is CO2 sink recarbonation, so it is almost 39% perhaps. So 39% potential is lying in the concrete sector. And CCUS, you can see 36%. So only by the clinker substitution or by any other means in the cement sector, we cannot achieve the net zero target. So we will have to take the CCUS, which is a major potential in the cement industry, or taking other industry as well together, and concrete industry particularly. So without taking concrete industry, we cannot achieve. That was my statement in the beginning, and this data proves that statement, that we have to take the cement industry, concrete industry, and construction industry together to achieve this target of net zero. Now, what is carbon capture utilization and carbon capture storage is, from flue gases, first step is to separate the carbon dioxide, 100% pure carbon dioxide, so that it can be used, and the rest of the component, and this carbon dioxide shall be taken to the site where it can be stored or it can be utilized. So we can see the typical flue gases composition: 18% CO2, 10% O2, and rest nitrogen and other gases. So to capture carbon and separating it, this is the process: concentrated CO2, 100%, and this remaining will be in the CO2-free flue gases. So how to separate? So there are three technologies we can see, if we broadly classify. So this is post-combustion. In post-combustion, from flue gases, it can be by calcium looping, or chilled ammonia process, or chemical absorption, or solvent-based absorption. But another way is to separate the carbon dioxide altogether. So what will be? It will be as a supply of air, in place of air, we can supply the pure oxygen, so that the pure CO2 will be available. So in that case, it will not be required to separate them together to use. And another one is pre-combustion. We can classify the fuel, gasify the fuel, and producing hydrogen, and that will be a clean fuel, and that can be used. And in that case, again, the 100% CO2 will be available, pure CO2, which can be used further. So this is the process of capturing pure CO2 or segregating pure CO2. And these are the technology available. These are the technology available world over. And we can see the cost of CO2 per ton of captured CO2. So this, while capturing the CO2, this cost, if it will be added together in cement production, that will be a significant cost. So how to take it forward? So one thing is capture and utilize the CO2 or stabilize the CO2 in non-valuable products. And another is try to stabilize it in a valuable product. And out of that valuable product, we will achieve some economic benefit. And that economic benefit can be subtracted to this. So that can be a viable option. So I am not reading every technology. This is available in the literatures. So now come to the utilization, as I was speaking. So how we can utilize that? So utilization possibility is so many. And out of that, mineral carbonation, which is in circle, mineral carbonation is one route, which is being utilized. Other routes are biological conversion, or food products, or enhanced fuel recovery, or plastics, or fire suppression, or inerting agent, or miscellaneous refrigerant, I mean to say chemicals, particularly in fertilizers industry. So we can convert this CO2 in a different form. I have visited one plant at USA, and they were making a wonderful food products, but they could not allow us to enter inside the concrete, inside the premises. But they explained how they are using this CO2, which they are capturing and converting into valuable product in terms of food products. So they were having more value. So out of this, role of CO2 mineralization in decarbonization of cement production, CO2 mineralization or mineral carbonation, it is a process of CO2 in the form of carbonates, converting metal oxides into carbonates. And calcium or magnesium carbonates particularly are poorly soluble, and therefore thermodynamically it is stable and thus provide permanent storage solution for the CO2. So this is about the mineral carbonation.
To conclude.
Yes, just I am concluding it. And this is the metal oxide, and CO2 converts into metal carbonate. So the mineral carbonation, one of the way is to expose these other waste materials, or BFS slag, or ladle slag, or EF slag, or paper mill slag. All these waste materials can be exposed with the carbon dioxide environment. Of course, mechanization is required, and this will be converted into a product which can be used in the construction industry either as an aggregate or in some way. So these are the value-added product, and these are the naturally occurring chemistry of mineral carbonation. Wilstonite or serpentite or olivine reacts with the CO2 and converts into the corresponding carbonate, which can be stabilize the CO2. And these are the chemistry of mineral carbonation of concrete versus. So concrete can be like calcium hydroxide or CHS gel. When exposed to the carbon dioxide, it converts it into the carbonates. So even anthracite, when it is exposed, it can form the gypsum and alumina gel. So this is about the concrete. And mineral carbonation at NCCBM, we have taken few projects where we are using the CO2 and infusing the CO2 in a fresh state of concrete, and after that in hardened concrete also. So we are evaluating what is the potential of carbon dioxide uptake in the concrete per ton of concrete. So what is that? Because without quantification, we cannot do the justice. So making a valuable product, but without accounting what is the uptake per ton of material, that is must to evaluate this. And the second project we have taken, the mineral carbonation of the waste material, as I was explaining. So these two products has been taken up at NCCBM. And these are the technology available for mineral carbonation. Again, I am not reading it because of, so these are the way forward. We should have a joint project with the cement industry, concrete industry together, with academia together also, so that we can do justice at our country level. This is required perhaps. So thank you very much from my side. It was some of the part of literature survey and some of the what NCB is doing in these terms. Thank you very much.
Yeah, thank you, Mr. Oza, for explaining the CCUS and the research what currently NCCBM is doing. So may I request the next presenter, Mr. Shri Annamalai. He'll be presenting on March towards net zero carbon emission through sustainability audits and process optimization from FLA Smith.
Yeah.
With the approval of the chairman, I am taking 1 minute time. That is very important also. So we will start the program exactly by 9. I request my all Indian delegates to come before times, because all important sessions are there. Yesterday, one session delayed by 5 minutes, delayed by 30 minutes. So today and onwards, tomorrow and day after, please come before time. People have already come from Mumbai. From early morning 3 a.m., they have already reached it. And after this session, the important sessions are there by the keynote speakers, and panel, also moderator, panel discussion. So all the important people from the Government of India is joining. So this is an honest request to the people to come before time. Thank you very much.
Good morning all. Myself, S. Srinivasan from FL Smith, taking care of sustainability audits. In sustainability audits, we support cement industry to reach their Mission Zero goal through our sustainability audits, which is also our FL Smith vision of Mission Zero, to reach net zero carbon emission. for cement and mining industries. We support sustainability audits for all cement industries. Till now, we have completed around more than 600 sustainability system audits, reducing the CO2 emission in various sections of the cement plant. So whenever we do a sustainability audits, we also focus on the major pain points which are in the cement plant. Plant will be facing various pain points, that is a higher power consumption, higher fuel consumption, lower waste heat recovery, lower utilization of alternate fuel, or a high wear rate, low recuperation efficiency, or high gaseous emissions, that is SOx, NOx emission. So we address those pain points through our sustainability audits. And also, we provide them guaranteed optimization services. So there are various 5 major levers in reaching the mission zero, net zero carbon emission. What are those 5 major levers are? Lever 1, energy efficiency. Whenever we do a optimization service, we focus on reducing the power consumption, either it could be a grinding system or a pyro process. We reduce the power and fuel consumption through our optimization audit services. In lever 2, that is increasing the TSR percentage. Recently, we have joined hand with the CII to provide end-to-end solution to enhance the TSR percentage in a cement plant. Lever 3, we reduce SOx, NOx emission. We have a primary mitigation solution to reduce NOx emission. We have done more than 50 primary mitigation through to reduce the NOx emission in cement industries. Around 25 to 40% NOx has been reduced from the base level at 10% O2 level through primary mitigation without injection of aqueous ammonia solution. In lever 4, waste heat recovery optimization, we do in 2 types of waste heat recovery, that is pre-assessment. Before installing waste heat recovery, we do a process audit and a layout to get the maximum waste heat recovery out of the existing system. And whenever, if already a waste heat recovery system is running, we do an audit to optimize the system to get more power generation. Finally, the lever 5, clay calcination as well as SEM substitute to reduce the CO2 emission. So already FL we have given a presentation on clay calcination. So through our sustainability audits in pyro process to reduce the power consumption, we do an audit. After the audit, we study the design of the system and give a tailor-made solution to reduce the pressure drop across the cyclone. This is one of the case study where we have done audit come CFD study to reduce the pressure drop across the preheater cyclones. So reduction in specific power consumption was around 0.5 to 1 kilowatt hour per ton in one cyclone. If it is a 6-stage preheater, a single string 6-stage, around 0.4 to 4.5 kilowatt hour per ton potential will be there. So the next is also the, all our solution after the audit will be to do a in-house modification plant. They themselves can implement those solutions to fetch the low-hanging fruits. We give 3 types of solution. One is mid-term, long-term, and short-term recommendations. In short-term plant, they themselves can implement the recommendations we provide in our audit. And mid-term will be having short investment recommendations, and major investment will be given in the long-term solutions. So here in one of the plants, we have relocated the distribution box in a preheater cyclone. That is, we have lowered down the preheater cyclone based on the FL Smith norms, and then increased the residence time in the riser to improve the heat transfer efficiency so that the power consumption has been reduced. So in one of the plants to reduce the high pressure drop from preheater outlet cyclone to downcomer duct was huge, around 120 mmWg. So after audit, we have conducted a CFD study to reduce the pressure drop. We have provided them some solution to implement. After implementing the solution, achieved a reduction in power consumption of around 0.4 kilowatt hour per ton in preheater fan. This is another solution. So there will be a huge false air at various sections of the cement plant. During our audit, we evaluate the false air ingress through inlet and outlet seal. So based on the condition of the inlet seals, we recommend to replace it. So after replacing the inlet and outlet seal, there is a huge potential in reducing the power as well as fuel consumption. In one of the plant, after replacing the kiln inlet seal, the fuel consumption reduction achieved was 5.5 kilocalorie per kg clinker, and the preheater fan power consumption reduced by 0.24 kilowatt hour per ton of cement. Yeah, this is another audit services, that is cooler optimization. It's an FL Smith SF crossbar cooler, where we have conducted the audit and optimized the cooler. During the optimization service, we conduct this type of service in 2 phases. In phase 1, we assess the process conditions and find out what are the bottlenecks in the system. Then we recommend them to do some modifications during the upcoming shutdown. After that, again, our team will reach the site and do the optimization services and provide the whatever the benefits has been achieved, which was evaluated before the shutdown. So here, after optimizing the SF cooler, the fuel consumption reduction was around 8 kilocalorie per kg clinker. In another plant, we have optimized the blending silo or increased the blending silo efficiency to reduce the kiln feed LSF variation. So earlier that plant was having a huge LSF variation of 5. From 97 to 93 was the LSF variation. Then we have audited and optimized the efficiency blending silo. Some corrections we have done process wise. So after that, there is a reduction in LSF variation of around 95.5 to 94.5. So there was a huge savings in the fuel consumption after reducing the LSF variation. We also do extend our audit services to other OEM design grinding system. In one of the plant, we have audited and found that a huge potential was available in the mill. So in order to exploit the available potential, we have optimized the mill to enhance the output. After our audit services and implementing the recommendation, the increase in our mill output was around 20%, and the reduction in power consumption was around 0.69 kilowatt hour per ton of material. It is a raw grinding ball mill system where we have done the audit services. After that, implementing the recommendation, the output has increased by from 8% on the same product residue, the output has increased by 22%. From 22% residue, the output has increased. Mill specific power consumption has reduced by 0.5. This is a CFD related audit services where the pressure drop in the various sections of the duct was high, and after implementing our solution, the raw mill specific power consumption has reduced by 0.3 kilowatt hour per ton of material. Again, it's an coal mill system. It's an Atax coal mill where the plant was interested to switch the type of coal from coal to petcoke. So they have to reduce the residue on the petcoke on 90 micron to improve the combustion efficiency. So we have done the optimization services and achieved the output without dropping the output, maintained the residue on petcoke. It's a cement grinding VRM optimization service. It's again FL Smith OK 39.4 mill, where the mill output achieved was 7%, and the reduction in power was 0.15 kilowatt hour per ton of PPC after the audit optimization. Again, it is a cement grinding ball mill system where our optimization has a yield output of 20% in the output, and the power has reduced by 1.5 kilowatt hour per ton on PPC basis. In AFR, we already indicated that we have joined hand with the CAI to provide a solution to enhance the TSR percentage. CAI, they will support us in pre-processing They will do a bed generators mapping in and around the cement plant of around 50, 100 and 200 kilometers and ensure to get the cement plant will get the consistent quality and quantity of alternate fuel. So FLSmith, we will be providing a solution for co-processing. So with these services, cement plant are getting an end-to-end solution to use alternate fuel and enhance the TSR percentage. So in one of the plant, we have done this type of services to increase the TSR percentage. Around 30% is the expected TSR percentage from the after these services. In NOx reduction, that is primary mitigation is our solution to reduce the NOx emission without using SNCR. So we can achieve 25 to 40% reduction in NOx emission through our primary mitigation. So in one of the plant, we have achieved around 40% reduction in NOx emission. So this is a comparison without having SNCR, around 7.16 crores per annum saving will be there through primary mitigation alone. That is savings in ammonia consumption. This is a waste heat recovery improvement audit, where after our audit and providing the solution, around 0.7 megawatt improvement plant has achieved through the waste heat recovery audit. Thank you.
Thank you. Thanks, Mr. Srinivasan. Now, I invite Mr. Roger for presentation on opportunities for CO2 reduction and higher efficiency.
So good morning, everybody. I hope you had a good rest last night and are fresh for my talk today. And also thank you very much to the NCB organization and the chairman and co-chairman for giving me the chance to give this talk today. So I would like to talk about opportunities to reduce the CO2 emission during the various process steps in the manufacturing of cement, combined with improved efficiency. In the talk, because FCT is pretty new for India, I would like to spend one slide showing a little bit about our company. Then I explain you the analyzer applications, and I would like at the end give you one example where we already implemented improvement in the case of raw meal preparation. So FCT AgTech is part of the FCT International Group. We have also a booth here outside D30, and if there are more questions, please come later and visit our booth. We have two more divisions. One is the combustion division, where we supply to the cement industry and minerals industry burner solutions, also solutions for calcining clays, etc. And then we have a third division, which is a little bit more exotic, and I'm sure you are not aware of that, but you might have seen our products because we make also pyro shows. The big breakthrough we had was in 2000 at the Olympic Games in Sydney, where we were honored with the order to do all the fireworks there. The last big project we had was at some sports event in Saudi Arabia, which was also very impressive. So if there is a need, feel free to contact us. Now coming to our analyzers, and myself being for more than 30 years busy with the analytical tools in the cement industry, most of the times you find that there are brilliant analytical solutions, but the big problem there is sometimes they are very complicated and it's very difficult to maintain them and keep them up and running. For that reason, and we are already more than 20 years busy in that field, we had a latest generation of analyzers which are very simple, but they are fit for the purpose. Of course, these analyzers, they should be also affordable, and also the installation should take not too much efforts. Usually such an installation will take you less than a week on site to get it from the delivery up and running. On this slide, you see how the analyzers look like. So these are not laboratory analyzers. This is equipment which is designed for the harsh environment in your production area. The size of such an analyzer is approximately 80 by 60 by 70 centimeters, so it's very compact. You see on the back side of the analyzer that we cover the analyzer with some isolation. The whole space in the isolation is temperature stabilized using the Peltier element, which can heat and cool. So there is no expensive air conditioning or other tools required. Simply, if you put it in a shack and prevent the analyzer from direct sun and rain, this is sufficient. You see on the right-hand side a pipe coming out of the analyzer, and that is also the new approach which we try to share with you, because these analyzers, they do not need any additional sample preparation, except in case of clinker where you need a primary crusher. But for all other free-flowing powder materials, they can go directly in the analyzer, and at the lower part of the analyzer we have a return feed system, so the sample or the material will be directly fed back to the process after the analysis happened. Of course, there is also a possibility to keep some sample for later analysis in the lab and also for the outer loop control. This is a look inside the analyzer, and that is also very different from the approaches of all other X-ray suppliers. We do not work with a press pellet. We work with a material stream on a rotating disc. So you see here the cement powder, and the cement powder goes continuously through the analyzer, and therefore we have much, much better particle statistics, which enables us also to allow slightly bigger particle sizes for the analysis without a compromise in respect of the analytical performance. So at the end of the day, you measure 20 to 50 times more material, you have much faster result. Usually from sampling to the feedback of the analysis, it takes only 10 minutes. Therefore, this is a prerequisite to do all the other improvements, because you have to know what's going on to be really able to improve. Now, we see these type of analyzers situated at 4 positions in the process. The first one is at or after the raw mill, to simply improve the consistency and the targets of the raw mill preparation. The second position is at the preheater, and that is more or less for 2 purposes. On the one hand, it gives you a very good overview what's going on in the preheater, so you will see directly the degree of calcination, and that is a very important screw for you to optimize the process there. Of course, nowadays, there were more and more alternative fuels used, and this causes, in some sites, also issues. There is a lot of chlorine, sulfur, and other elements going into the process that can cause clogging and interrupting the whole process. By using these type of analyzers, you can either look on the chemistry or you look on the mineralogy and take corrective actions in advance to avoid this trouble. The next position is after the clinker crusher, where you simply see the halide and the free lime to optimize your process. And the last and also very important position in the process is the final check of the product, the cement. And the results from that can be used in various ways. For example, you can reduce the clinker factor, control your additions like blast furnace slag, that you guarantee a very consistent quality for your customer. To achieve this, we have more or less 3 different types of machines. We have pure XRD machines that tell you the mineralogy. We have pure XRF-based machines to explain you the, more or less which elements and in which quantities are in your material flow. And we have the combined machines with advantages that can be used in various ways, as I told you already. Now I would like to focus a little bit on our raw mill analyzer. That's a picture how the analyzer looks like without the enclosure and without the support machine. Usually you constantly feed the sample into the pipe. The whole process is fully automatic. and the sensors tell the plant PLC when to send material, when not, because we always want to have very fresh material inside, that you get almost real-time information about your process. This is from one installation in the US, where we take the sample continuously from an air slide, and then if you look on the left picture where the yellow arrow is located, that's the position of the sampler, and underneath we protect the analyzer in a little bit of shack, so the material falls down in a tube, goes directly in the analyzer, and gives you wonderful results in real time. Usually with this type of approach, you can get a result every second minute. And that is a wonderful tool for you to improve the consistency of your raw mill. This machine is fully integrated into the automation process in your plant, so it requires no manpower on the routine operation, only about 20 minutes per week to do some cleaning and preventive maintenance. So the cost of ownership is very, very little. It consumes only a little bit electricity and no other things are required for that. The PLC from the plant tells the analyzer when material is flowing. This initiates the sampling process. Sample goes in the analyzer, and with a return blower system, it's fed back to the process. Here are some results from this customer. You see in the middle of the graph, the black line indicates when they introduced the analyzer to their process. So you saw, in particular on the silicon, you saw quite huge, let's say, oscillations. And we all know if there are oscillations or changes in the product streams, it requires more energy. And it will increase also the wear on the equipment. And you see clearly after the analyzer is installed, you smoothen the behavior of the variations, and this gives you various opportunities. Of course, today the time is very limited, but if you have more questions, please come to our booth and we can discuss it. In this specific installation, the customer was able to produce with the same input a higher quality clinker. So you see here that before the halide concentration in the clinker was lower. After the installation it was much higher, and this enabled the customer on the one hand to produce a very consistent product, but also to add more additions and therefore directly reduce the CO2 footprint of the production. So in this talk, I hope I showed you and stimulated some of the opportunities. Feel free to visit us at the booth outside, D30. And with our wonderful team here in India from Icon Scientific Systems, I'm sure we can find a proper solution for you, and we find the best way to optimize all your processes on a short term. Thank you for the attention.
Thank you.
Yeah, thank you, Mr. Roger Meyer, for sharing the product details. Now I request Mr. Arup Das to present on a paper Green Cement Plant Technologies for the Sustainable Use of Resources at Lowest Emissions from ThyssenKrupp Industrial Solutions. What we'll do, just to ensure that the time is precious to everyone, we'll put the first bell after 8 minutes so that you are aware that you have 2 minutes left. So
okay.
We'll put
okay,
bell
no
after
problem.
the 8 minutes.
I will ensure that we finish before that. Okay, good morning everyone. My name is Anup Das. I work in the Process Engineering Department of CCUS Industries, India. Today I have the product portfolio, the overview of product portfolio which we have for the green technologies. So we all know what we are responsible for, that we are responsible for 7% of the CO2 emission, and that is why we are all striving to shift from grey towards green cement. The unfortunate part of cement industry is that the CO2, maximum percentage of the CO2 is coming from the raw material itself. The strive for SCM material is already there, And we have this solution for calcium-activated clay technology, which we'll have a look into. Then the second immediate step would be to go for substitution of fossil fuels and higher degree of TSO. Even after that, if we have some CO2, which will definitely be there, we have also some technology and under development stage, let's say, to capture those CO2, and we can improve the concentration level of CO2 in the exit gas. We first take the immediate step of our pre-pole SC. We call it the step combustor. This is an additional combustion chamber which is attached to our calciner to give us ample residence time. We are not talking in terms of seconds, we are talking in terms of minutes. We are talking in terms of 15 minutes or 1,000 seconds of residence time. The beauty of this system is that we have no rotating machineries inside the combustion chamber. At the same time, we have continuous churning of the alternate fuel, which gets always a second chance to get mixed with the hot tertiary air. And thus, we can ensure that we have almost 80 to 90% combustion already taken place before the material is getting into the calciner. Okay, I will skip these slides, the theoretical, the R&D processes which took place before we reached to this design. I just wanted to inform you that we have already 10 installations in working condition and 7 are under execution. And in this chamber, we are talking of feed size up to 300 millimeter. Well, then the next topic is to go towards substitution of clinker itself. And for that, we have our activated clay technologies, which is Polcal technology, basically flash calciner to activate the kaolinite, and so that we can replace the clinker percentage. Okay, here is a flow sheet which shows the basic principles of a flash calcining technology, but at the same time, if required, we are also, we can take up rotary kiln technology as well. The first plant for this technology is under execution in Cameroon with 720 tons per day calcined clay production. So this some analysis that if we are replacing clinker 30% by calcined clay, there are chances that we can reduce 25%, more than 25% CO2 emission. But we know that even after that, we will have some CO2 coming out of preheated tower. If we want to capture that, we need to increase the concentration level of CO2. For that, we have our oxy-fuel technology, pure oxygen for the combustion of inside the kiln. And in second generation, as you can see here, that the first generation where we are expecting around 80% CO2 concentration, but in second generation, we are going more than 90% concentration level, with which 20 to 30% power savings will be possible in the CPU unit. On the right-hand side, you can see the expected cost factor when you compare with other available technologies. This oxy-fuel second generation, this is working out to be the cheapest one, but okay, we probably have some years to go till we go there, because the business case will be fruitful only when we have negative pricing for CO2 capture. We are available at our booth outside on the ground floor. If you want to have more detailed information on these technologies, we are available there. You are welcome. Thank you very much.
Thanks, Mr. Arup Das. Now I invite Mr. L.P. Singh and Mr. U. Sharma for presentation on mitigating climate change through low-carbon research initiatives in building materials. Mr. Singh and Mr. Sharma.
Okay.
Good morning. My name is LP Singh, and I'm working as a senior principal scientist at one of the premier laboratory of CSIR, that is Central Building Research Institute, Roorkee. In the very beginning, Dr. Ojha probably set the tone for this session, that what are the decarbonizing efforts that are being taken care of across the globe as well as in the country. So I will just go a little bit deeper into that what are the research that we are pursuing at CSIR CBRI. So just to start, for the last one day, I'm seeing a lot of pressure on cement industry. But believe me, cement has been a wonderful material, and it will continue to remain a wonderful material. Of course, some siblings like geopolymer, LC3 will come, but cement will remain the eldest brother. And of course, in the current scenario, there are issues with sustainability, and especially on climate change. So, but still I see a very good silver lining that in spite of, you will see there are many efforts that are being made to reduce the temperature to below 1.5 degree centigrade to the, that is pre-industrial level. So there are many technologies on CCUS that are working, making like methanol, ethanol, making proteins, carbohydrates. So many things are there in the market. But still, if you look into the future forecast, the maximum amount of CO2 that can be captured, stored, or sequestered is again the building materials only. So if we talk only the cement, of course cement is producing CO2, but if you look into the circular economy where the cement is being used, the ultimate material is the concrete. You will find that we can not only make concrete zero carbon, but if with proper R&D, in fact, your concrete can be carbon negative too. So it will also have the space to capture CO2 for that is emitting out of from other sources. So this slide probably Ojha Saab already shown that whatever cement industries are trying, whether it is in terms of thermal efficiency, fuel switching, reducing the clinker. So whatever efforts we made, we cannot cross more than 50%. So still there is a lot of scope for innovation, and probably one of the area that we can think of is the carbon capture. So at CBRI, we are working on 2-3 areas. One is development of artificial aggregate through carbon sequestration using kind of waste that could be fly ash, slag, and many kind of lime sludges. Then we are also trying to do some research with preparing some kind of low carbon cements. And as this conference says, other building materials. So there is another very important material, that is bricks. In India, we have huge quantity of bricks manufacturing, and probably very little is being thought of that how we can improve the efficiency of brick kilns. So if we talk about the international scenario, some companies like Calera Corporation, Blue Planet, Carbon 8, they have already achieved a level of TRL level of 8 to 9. So they are at pilot plant level, and of course 1 or 2 company has already started production. So most of the things, if you are looking in terms of innovation, are covered under the patent. Means you think of any waste, any combination, so it is covered under the patent. So, and they are making kind of products like aggregates and many kind of building products like roofs, roof tiles, paving blocks, bricks, etc. So these technologies are slightly popping up at international level. And India also, institutions like NCCBM or CBRI, they are trying to come up with some innovative approach that how we can use these kind of what internationally going on, that what is the science behind it and how we can innovatively come up in India on these aspects. So if I talk about one of the technology, that is Carbon 8, they use industrial waste, primarily fly ash, and India, we have a lot of fly ash available, And when I'm talking about fly ash, I'm not talking about the fine quality of fly ash, I'm talking about the pond ash. So that is available. And international research says that we can make aggregate out of it. This carbonate system has potential to capture 1 million ton of carbon dioxide per year. We are also making efforts in this direction. I will show you some of the slides. Then another technology is basically Blue Planet and Kellara Corporation. This technology is basically using seawater. So probably for a country like India, this may not be very much applicable, but they have very high quantity of CO2 uptake. Means, see, aggregate can be made, but the challenge for the researchers is how much CO2 can be captured by the aggregate. So at CBRI, we are trying that because Blue Planet or carbonate has achieved around 8 to 10%. So we are trying to achieve more than this. We are actually have ambitious target of capturing more than 20%. So this slide, I have only taken from the internet. So as I mentioned that cement, as you normally say, concrete has a positive carbon footprint around 360 kilogram of carbon dioxide per meter of concrete. But if we use low carbon cement technologies, if we use aggregates that has CO2 sequestered aggregate basically, we can not only make our concrete carbon neutral, we can in fact make our concrete, what we call it, carbon sink, carbon negative. So CBRI for making aggregates, and when I'm talking about the aggregates, I'm talking about the initially lightweight aggregates, ultimately to make lightweight bricks blocks or lightweight concrete. So there are two technologies. One is fly ash sintered aggregate, and the second technology is the clay aggregates. So these are the two established companies in the country. So we at CBRI also trying to make aggregate with fly ash using, and we are making aggregate, and then we are looking into that what are the carbonatable phases that are forming during this process. And we have to achieve, as I mentioned, how much more and more amount of CO2 can be sequestered. And we know that phases like valsonite, pseudo-valsonite, or calcium aluminosilicate are the phases that you require to have more and more amount of CO2. So when we are then, once aggregates are prepared, we are trying different ways how we can put carbon dioxide into it. So at laboratory level, we are trying direct carbonation. We are trying to have some kind of solution prepared, and we are also trying to make some kind of slurry of lime slurry, and then we are trying to achieve it. And probably if I have a slide, I will show. We have achieved almost more than 20% CO2 can be sequestered when we are using slurry of some calcium material like we were using actually calcium carbide, right? So these are some of the engineering properties of this aggregate, and you will see lower slide if you see pellet strength. Means I am comparing it, as I mentioned, the lightweight aggregate that are commercially available. Then the third column you will see is the synthetic limestone aggregate that is carbonate at international level they are preparing, and what we are doing at CBRI. So you will see that we have higher single pellet strength as compared to what is available in the market. And then you will see CO2 uptake with synthetic limestone aggregate. You will see they have around 7 to 8% CO2 uptake. We have already achieved 9 to 12%, and we are trying to more that how more and more CO2 can be uptaken. Then second area that we are working is on the development of cementitious material which has low carbon footprint. This is basically Solidia technology. I think there is a presentation by Solidia also. So we are also trying to understand what is the chemistry behind it. And as you know that normal cement is produced at 1450. So, and Solidia is around 1200 or 1250. So we are trying to understand that how even we can bring down the temperature, and we are also trying to use different grade of limestone. So this is what we are trying to do at using with different grade of limestone, and we are trying to prepare at CBRI, some kind of technologies only. Thank you. The last technology which has actually gone to the field, I will just summarize. Brick is one of the biggest sector in India, and we are producing around 250,000 crores of bricks in India per year. We have more than 100,000 of bricks. But there is a lot of problem with the brick industry that they have insufficient combustion, and they have a higher amount of that what we call energy consumption also. So in Delhi NCR region, 2 years back, NGT banned all the brick kilns by stating that breathing is more important than manufacturing the bricks. So that means 3,000 brick kilns were closed. So then we received a letter from Honorable Minister, and NGT mentioned that you have to come out, either you have to work on brick kilns with PNG, CNG, or any other alternate technologies. So most of the brick kilns are operated in rural areas. So many of the brick kilns do not have even electricity, so forget about PNG and CNG. So we were thinking that what kind of innovation we can do, and we know this is a rural-based technology. So whatever innovation is to be done, with minimum intervention and maximum benefit we have to do with that. So this is basically a manual process, how we manufacture the brick. And what we know that when you are manually manufacturing the bricks, we have a moisture content of around 20 to 25%. So we are changing the process with machine-made bricks. And in machine-made bricks, we have only the moisture content of 8 to 10%. So this difference in moisture content, 20 to 25% versus 8 to 10%, we are taking advantage of it. And what we are doing, we are using internal fuel. So internal fuel means that we are using reject coal. And when we are using a reject coal, why? Because it has a medium calorific value, around 2,000 to 2,500. So what happens when we are making powder of this coal, mixing with the soil mass? So when bricks are burnt in the kiln, you do not need to put external fuel, external coal from outside. So coal is available within the brick bodies.
Please.
Just 30 seconds. So so bricks are produced with internal coal only, and you do not need to put external coal. So what it does, that whatever ash is produced, it is kept inside the brick, it is left inside the brick only. So it has saving in terms of air pollution, and it has saving in terms of coal consumption also. So we have done calculation on this, and we have also found that whatever you invest on mechanization process, because mechanization takes around 20 to 30 lakh rupees, so that is you get back it within 1 or 2 years only. So this is one of the technology we have already demonstrated at 2 places in our NCR region. And this year we are going to propagate this technology, and this technology is going to have a big, what we call about low carbon, because it will have saving in coal consumption, it will have reduction in suspended particulate matter and carbon emission, it will have higher profit for the brick kiln owners, and last but not least, the low CO2 emission. Thank you very much.
Yeah, thank you, Mr. L.P. Singh. Now I request Mr. Prasanna Kumar from Dalmia Cement to present the Dalmia RPG carbon footprint roadmap.
Good morning, all dignitaries. Myself, Prasanna Kumar from Dalmia Cement, Rajgangpur unit, Orissa. So I am here to present a paper on carbon footprint reduction. What are the activities we are doing practically in our plant, and how we are achieving the target, and what are all the practical challenges we are facing here. So first of all, so this is our overall plant setup. We are having 3 lines of clinkerization unit and grinding units, approximately 6 million ton per annum. And we are producing green power of 24 megawatt, which consists of WHR and solar units. And we are also having a thermal power plant of 54 megawatt capacity, and it is running at 40% AFR. So almost 43% of the power production we are managing from our green power. And this is the roadmap, carbon footprint roadmap. Here you can see we are gradually reducing year by year, and we have targeted for carbon neutral by FY30, and afterwards carbon negative. So these are all the few activities in which we are working. So briefly I want to say, we are maximizing low carbon cement production by maximizing the blended cement production in our plant. And we are also maximizing the AFR and green fuel such as biomass, municipal waste and liquid wastages. And we are also maximizing green power energy through our roadmap of solar power plant installation and WHR installations. Also the green energy usage is gradually getting increased. And one more area which we are working is we are gradually changing our fleet of vehicles for mines movement, raw material movement as electric vehicles. So already we have started this mission, and we are already introduced 4 trucks in our unit which are successfully running. And one more area, nature-based solution which we are working, we are rigorously improving our plantation. We have planted 30,000 trees last year, and we have targeted for 50,000 plantations this year. Also, for new technologies, we are working with our strategic partners for installation of CCUS in our plant. The work is under progress. This engineering work is under progress. Hope we will install some units by FY30. So in the next slides, we will see some practical usages. This is our green fuel area which we are working out. So you can see how we have been reducing this carbon emission. We have increased the reduction by 3 folds in the last 3 financial years. Also, how we are achieving this? So we have installed a state-of-art AFR system for handling solid and liquid waste. So in this, we have been facing a lot of challenges. Now also we are facing, and practically we are finding solutions to increase our increase the usage of these alternative fuels. So the challenges what we are facing is the segregation is the first challenge, because whatever the fuel AFR and green fuel which is coming to our plant, it is from municipal waste or industry rejects and this hazardous waste, everything. So first of all, the segregation is a major activity, because segregation and usage, this we are working and we are facing challenges, and we have come up with some solutions. And one more thing, since the fuel which is coming, it is with contamination and lot of mud. So this is increasing the abrasion rate in our machineries, including shredders and cranes, everything. So one more problem which we are facing is operational disturbances. Since this is not a homogeneous mixture of fuel, so a lot of operational disturbances are come, and gradually we are getting accustomed to it, and gradually we are stabilizing the process. And next is the viscosity and CV variation from liquid fuels. One more problem is since we are handling this municipal wastes and hazardous waste also, so 2 problematic areas are the smell and the safety. So we have installed air curtains in the areas which this wastages are being used, and the space has been strategically designed that it does not disturb the plant operations and nearby persons working there. And for safety, we are doing hazard study in the areas regularly, and frequent monitoring and education is given to the people working over there, so that it is safe to work. Also, we are working in capacity enhancement in the plants to reduce our specific power consumption and specific heat consumptions. So already we are in the process of increasing the capacity of one of our units, and one more unit, the engineering work is under progress, and by FY25 we will do that work also. So one more area where we are working is the chlorine bypass system, so that the chlorine which is coming with the AFR, that can be captured, and that will not affect the quality of the cement. This work is also under progress. So the major area, one more which we are working with, is production of blended cement, and also optimizing the CC ratio. So we have almost achieved this target. We have almost stopped the production of OPC, and we are producing blended cement only in our plant. And because of blended cement, the inherent advantages which we know is it saves the natural resources, the raw material which is required is less, and energy consumption is less. Also conserves water when using this. Also this through this is protecting the environment. So we strongly believe in production and usage of blended cement, which we have taken it as a mission, and we have taken up with our customers also for making them understand that blended cement is good for their construction also. So this area is with respect to green energy. Already, as I have said, we have installed WHRS units in 2 of our plants, 2 of our units. We are having 3 units, and 2 units we have already installed. By FY19, we have installed 1 plant, and FY22, we have installed other plant. And we are generating 22 megawatt of the WHRS systems. So this is fulfilling our 43% of our power demand. And we have saved this much of fuel, which you can see in the slides. We have saved fossil fuel because of the WHRS. And inherent advantage of this WHR is power cost is already less, and carbon emissions are coming down drastically. In green energy area, one more area I would like to mention, we are rigorously in Dalmia Group, we are going for solar power generation. So we have already installed solar power generation in our site and our Cuttack unit also, comprising of 20 megawatt of solar generation. So we are also looking for further sites for solar installations. So this solar installation we are planning by FY30, we will be using 53% of solar generation for our cement production. So this much of fossil fuel we have saved through our solar power plants. This is our green power roadmap. So as I said, presently we are at 42% of green power, and by FY25 we are planning it to increase by 46% by installation of 5 megawatt solar power at our site. And furthermore, we are planning to install solar plant, off-site solar plants for satisfying our requirements, fulfilling our requirements in plant. So the challenges which we are facing in solar plant is power at non-sunny hours and night times. So we have 2 options for this. One is we are working for banking option. So this is the area which has to be worked out along with government agencies. So if banking option is available, we can install solar power plant, and that can be used at night. And one more option which we are working, we have started, this is a very nascent technology for battery usage, so to store power. This is a very new technology, and we are working it at using battery banks. It is at a very initial stage. If it will be successful, then we will be going to 54% solar power for our demands. So one more area which I said is this electric vehicles. So we have been successfully using this electric vehicles for the past 1.5 years. In India, Dalmia Cement is the first plant to use e-trucks. And this e-trucks, we have already introduced 4 e-trucks in our plant, and they have been successfully working for the past 1.5 years. And we have a fleet of 22 trucks. So we are planning to completely change all these trucks for raw material movement and mines movement. So this we have targeted by FY30 to completely change our fleet to electric vehicles. So this is our summarized roadmap, which I have explained all the time. This is we are going for 100% blended cement and 100% renewable energy we are targeting by 2030. And we are doubling our green power energy by solar plants. And also electric vehicle, as I said, we will be going to the transition by 2030. And we have planned for 100% TSR usage by 2035. Also this carbon capture, utilization and storage, this is at the very preliminary stage, and we are working with our strategic partners. Thank you, one and all. Thank you, sir.
Thanks, Mr. Prasanna. Now we invite Mr. V. Ganeshan and Mr. Demla for presentation on where to augment green power production case study of Chettinad Cement.
Good morning to all of you. I'm Ganeshan from Chettinad Cements Corporation, Private Limited, formerly known as Chettinad Cements Corporation Limited. We entered into the cement industry in the year 1962. Our first company started in the year 1968 at Puliur in southern India. We scaled up our capacity to 25 million tons. Today we are sitting with 25 million tons. We have got plants mostly having maximum capacity in Tamil Nadu, followed with Andhra, Karnataka and Maharashtra. Maharashtra we have a grinding unit, and Vizag we are also having a grinding unit. The company is one of the flagship company steered by Mr. M.A.M.R. Muthaiya, who is a pragmatic and visionary leadership. The company started with a very, very small capacity, modest beginning with 2 lakh tons. Today we have 25 lakh tons, 25 million tons, which shows clearly that we are progressing very well. We are also not only in the business of cement, we are in the business of granite, we manufacture silica, we are in logistics, we are in shipping, plantations, power, transportation, stevedoring, clearing, forwarding agents, everywhere. We have a capacity of 162 megawatt of power in our captive power plant, which caters to most of the power requirement of our cement plants, especially integrated plants, except for our Solapur grinding unit and Vizag grinding unit. We have a policy, and we started putting up solar power plants to a capacity of 6 megawatt, 3 megawatt at Kallur and 3 megawatt at Solapur. We are in the process of implementing 20 megawatt of solar power plant by end of 2023. We are also installed a waste heat recovery system to a capacity of 7.3 megawatt at Kallur and almost 19 megawatt at Dachapalli unit, which we will be discussing now. The company also started putting up an M-sand grinding unit, manufacturing of M-sand, P-sand, and also aggregates, which was a reject which was coming out from this plant. So when we decided to go with the Dachapalli plant, which we want to make sure that it's the most modern plant with all the technologies that can be incorporated, we partnered with KHD, and we decided to do a proper study right from the beginning of the plant, rather than the planning stage itself. Our main focus were energy conservation, operational cost reduction, better utilization of the resources that are available nearby, and reduction of greenhouse gas emissions. Keeping in view of all this, CCPL definitely has taken a leading role in selecting the suppliers right from the crusher up to WHRS. As far as KHD is concerned, KHD has been supplied equipment in raw material grinding, cement grinding, and complete pyro, including cooler. Let me just talk about raw mill. Raw mill, we had a normal roll press closed circuit mill. Taking into consideration of the very less moisture content of the raw material, we decided to go with the roll press finish mode, which had an advantage that we don't have to spray water. If at all, if you are going to have a vertical roller mill, you need to spray water. We were able to operate the mill with a very nominal temperatures of 85 to 90 degrees centigrade. So which has helped us to generate almost 1 to 2 megawatt of extra power, which otherwise we would have lost if we would have gone with a vertical roller mill. And there was also a provision wherein we can even bypass a small amount of the gases in case if the material's moisture goes up during the rainy season. That has been made. And the pressure drop in the system is definitely much lower, and the volume of the gases handled is also low. So naturally, this is an added advantage for us. So ingress of false air is also very less. So this is basically, we have 2 mills with 350 tons per hour capacity. As far as the pyro is concerned, we had a 2-stage preheater, 2-string preheater with 5-stage preheater, and which has got hardly a pressure drop of 300 mm water column. We have incorporated redox system, the first time in India, and we gave an order in the year 2017. We are the first people to accept the modification which was proposed in the system. And we could see, or rather we could reap the benefits in terms of introduction of redox in the system. It's basically a gasifying reactor. It reduces your NOx level to a tune of approximately 250 to 300 milligrams per normal meter cube. The advantage of this is that you have one gasifying reactor lying between your kiln inlet to the precalciner. So the lean gas which is coming out of the kiln, which has got very low oxygen content and CO2, the added advantage is that you will be feeding almost 30% of the raw meal, which acts as a catalyst. And also, it is also able to add 80 to 90% of your precalciner fuel with a sub-stoichiometry condition, wherein you form huge amount of CO. This CO which is formed actually converts your nitrous oxides back to nitrogen, and the system is designed in such a way that there is a sufficient amount of residence time of almost 4 seconds, which creates an environment for denoxing your nitrous oxides back to nitrogen, and it never goes back again to nitrous oxide. So this is an advantage. Because of this, after this reaction, when the nitrogen gets converted, it goes back again to your precalciner, what they call as pyroclone, where it is encountering high oxygen from the TAD, and again the real exothermic reaction happens, and your calcination is also happening. We have physically seen that if you don't operate pyroredox, and if you are operating only a pyroclone, definitely our NOx levels were quite high, which we could see. And the moment when we start doing this, the NOx levels comes almost very close to 250 to 300 milligrams per normal meter cube. This has got an added advantage in the sense that somebody was talking about SNCR, SCR, and also there are a lot of technologies which have come with burners, low NOx burners, and also stage burning in the precalciner. But whatever said and done, I feel this has got a better technology in the sense that we save a lot of money in terms of not only in the capital expenditure and also the revenue expenditure. In case of SNCR, you will be definitely pumping ammonia, which will be a slippage. And the ammonia slippage is again an headache. But this has got an added advantage, and I believe that this system should be very successful. And being a modular design, I understand that some of the places where in China, they have already installed and they are reaping the benefits. And more than 14 or 15 orders, I think he may be able to tell us how many orders he got in outside India. See, that's subsequent to that thing. The NOx abatement is going to be a biggest challenge in future. I'm 100% sure this is going to be a requirement, and there will be stringent norms are going to be enacted in the future, and we need to be very careful that we need to come down to the levels where international norms have to match, because mostly we are going towards international norms, so we need to be doing that. We also have a pyrojet burner, which is again a low NOx burner, which is using a very low amount of primary air, and it is quite reducing the NOx levels. The most important one which I want to talk about is the cooler. We have gone for a pyrostrip cooler of 215 meters square. The cooler has got one difference in compared to other coolers. We got two static grades. That means static starts with static, there is a dynamic, again there is a static grade, followed with a crusher. We find a very good disagglomeration of the clinker and better heat transfer, better recuperation efficiency that we could see. That's an advantage. And secondly, we are also able to have a crusher in between the third grade. That means before the third grade, we got a crusher. So we are able to get a better fragmentation and a better surface area exposure. And we could get more than about 1 to 1.5 megawatt extra because of this. And we are also doing one good thing is that we are almost recirculating 100% of the air which is coming out from the cooler vent, which is about 100 to 120 degrees centigrade, which is completely pumped in. So ultimately, we are able to generate from our WHRS almost 14 to 15 megawatt. Our power plant was supplied, WHR is supplied by ISJEC, and our boilers are supplied, the turbine is supplied by Siemens, where we have specifically asked for low pressure injection turbine, where we are able to get approximately 85 to 89% of our total power requirement of the cement plant. That's what we could get right now. We also, at the initial stage itself, we have put almost all our both medium voltage and low voltage motors with VFD. Almost 75 motors we have installed, and we could see a real benefit. And cement grinding, of course, it is a similar grinding with a roll press ball mill circuit, and we are able to get a better quality cement with a better particle size distribution. And we are also having a flexibility to run with roll press with closed circuit. This alternate fuel handling we have already installed. We have a Weimar, shredder, where we are able to shred most of the waste material, mostly municipal solid waste, multi-layer plastic, almost all the solid materials which we are able to shred and then we are able to feed. And this is the advantage, and we are able to substitute approximately 20% of our requirement of the fuel. With this, we are able to achieve a very good this thing. I expect Mr. Dembla to close the...
Only few words that with all this technology, I think he has talked about NOx reduction, water reduction because of roller press technology. I'll take 2 minutes only. And then waste heat recovery, we have already talked, almost 80%, AFR and energy conservation. In conclusion, we can say that we can design the system. First is Chettinad continuous development towards technology, and we could adopt pyroredox in this plant, and we could take all the steps. So these were all positive, and the plant is running almost at 10,000 sometimes, and it is a success story with low NOx and low carbon footprints. Thank you.
Thank you.
Thank you.
Yeah, thank you, Mr. Ganeshan and Mr. A.K. Dembla. Now I request Mr. K. Karpaga Jyoti to present the Dalmia Cement paper on moving towards a net zero carbon emission.
Happy morning to all. My name is K. Karpaga Jyoti. I am coming from Dalmia Cement, Dalmiapuram, Tamil Nadu plant. Our title is moving towards net zero carbon emission. In Dalmia Cement, already we have set aspirational goal to achieve net zero CO2 emission by 2040. In this presentation, we are going to see CO2 emission reduction by consuming biomass. In our power plant, we have taken a lot of initiatives to reduce the CO2 emission. Some of the initiatives, biomass consumption in our boiler, solar power installation, and WHRS installation, AFR in cement plant, and wind farm installation to utilize the wind energy. In our power plant, we are having 2 numbers of ABC boilers. Basically, these boilers designed for only imported coal and lignite. It is not designed for biomass. This is the overview of our power plant. Without any modification, in our boiler we started 5% TSR of with consuming rice husk and sawdust. After we discussed with our OEM, and we have modified our furnace to provide the overbed system through these are our biomass fuels. Below 6 mm size, we are directly using in underbed feeding system. After modifying our furnace, our TSR is going to 25% to 30%. These are the fuels: veneer waste, juliflora, wood waste, and wood bark, and polywood waste. This is our boiler, ABC boiler. In this, there is no provision for overbed feeding system. After that, we provided that red marked conveyor system with connected to the furnace. After this modification, we are consuming 30% of biomass in our boiler. Some of the photos: feeding conveyor, conveyor to chain conveyor to boiler furnace. When we are using biomass, we are having lot of constraints also. That mainly the biomass is having alkali content in the fuel. If the alkali content more than 5%, it will stick on the superheater coils. It will affect our boiler efficiency. One more constraint is lot of stones and mud material will come. For that, we have provided additional bed drains to remove the heavy particles from the bed. Last September onwards, we started September 21, we started the biomass without any modification, 5% TSR. Slowly we increased our biomass consumption. Now we are consuming 3,000 tons per month. Through this biomass consumption, we have reduced, we started with 1,000 tons per month. Now we are in 4,500 tons per month CO2 reduction. This is simply pie chart. Mainly biomass consumption, we have reduced 53% of CO2 and WHRS 32%, heat rate and auxiliary 4%, and solar generation 11%. This is already seen in the previous one. These are the initiatives. In boiler, only 3 potential is there: biomass consumption, auxiliary reduction, plant heat rate reduction. WHRS, already we have provided 6 megawatt WHRS in our Tamil Nadu plant. 5 megawatt solar plant commissioned and connected to the CPP. 16 megawatt plant is under progress. Wind energy also in progress. This is our biomass roadmap. We started FY21, 22.4%, and we are having proper roadmap up to 40% TSR. Some of the photos of 5 megawatt solar plant. And in Tamil Nadu, we are the first green power generator. We have provided a WHRS system in our plant, 6 megawatt WHRS plant. We are also having RE100 projections. In the 2030, we will maximum we will achieve the RE100. For that, 5 megawatt solar already commissioned, 6.5 megawatt wind farm in progress. 16 megawatt solar plant also in progress. 16.5 megawatt wind power also is in line. Conclusion: we are planning to improve our biomass consumption from 25 to 40%. System is under study. Clean and green is sustainable and profitable. That is responsible for our future generation. Thank you, sir.
Thank you. So, thanks, Mr. Jyoti. Now we invite Mr. Matthias from KHD for presentation on sustainable solution for net zero emissions, collaborative approach for green corridor.
Thank you very much, Mr. Chairman. Ladies and gentlemen, it's a pleasure and an honor for me to be here speaking to you about sustainable solutions for net zero emissions. As you will notice and as you know, this is a very decisive subject, and this is a huge challenge and task for us to find our way in the transformation into a low carbon or zero carbon industry. So I would like to start off with showing you a map of the world about 20,000 years ago. This is the Ice Age, the last Ice Age. And it covered the total area of Northern Europe and America, as you see, completely with ice. Now guess how many degrees centigrade it was colder than it was today. It is only 5 Kelvin colder than today. And it covered Northern Europe completely with ice. Now, these are pictures of a projection of the IPCC, what the world would look like if it was 2 Kelvin higher average temperature than today. And I'd like to draw your attention to the lower part of the map. And it shows the color scale is scaled to the days per year when air temperature and humidity conditions pose a risk of death. And look at the dark shades and the dark colors in India and the Southeast Pacific, Indonesia, Philippines. There's a high risk of deadly temperatures and deadly humidity conditions in India. And if I would have one wish for free, I would wish to forward this picture to Honorable Mr. Modi, because this is really a threat, and specifically to India. So we have to do what we can do in order to decarbonize our industry. Now, what can we do? We've been listening and presented by honorable and knowledgeable speakers about their proposals, and I think the range of technologies and options is so wide, I thought it might help to draw up some generalized diagram to show what options we have. Now, if we take a look at the whole value chain from raw material quarry to concrete, we start with our raw materials. I hope you can read it somehow. Then we talk about limestone, of course, traditionally, but we also talk about clay, we talk about waste products maybe that we could use for the production of cement, cured products and carbide slag, for example, somewhat exotic materials which we could use. Then we talk about raw grinding, and of course it's about efficiency. Saving any kilowatt hour for raw material grinding is an optimization. Then we talk about the whole aspect of clinker burning, the pyro plants. Of course, efficiency enhancement is a matter we have to follow. Low carbon fuels, pre-combustion technologies, we've been hearing about that this morning. Alternative fuels, huge topic. Oxy-fuel plants, we've heard about that, huge topic in the future. Carbon capture will be necessary to some technology, whatever, not necessarily only amine scrubbing. Calcium looping, and we talk about artificial intelligence, RTOs, runtime optimizers, anything that enhances optimal production. Cement grinding, it's about efficiency again, but it's also about lowering clinker factor. Concrete mixing, we can use carbonated materials. We heard about that this morning as well. And then it's about concrete curing, about binding CO2 during the curing process. Now, if we take a look at what are our options here to optimize in view of decarbonization, of course, we talk about aggregates being used for the concrete. We talk about additives to be used in the cement mill. We can talk about low-carbon industrial carbon-containing residues to be used as raw materials for the clinker production. Then we talk about the big subject of calcined clay. And then we talk about, finally, capturing gaseous CO2 emissions from the clinker burning process and use it, store it in several ways possible. We talk about industrial or natural oxides which we could use to carbonate them and then later on use them in concrete as aggregates. And we can even use spent concrete to do that. So there are lots of options when it comes to phasing in or phasing out CO2, or carbon-containing intermediate or byproducts, recycle them, and use them in order to close the carbon loop and finally reduce or completely omit the CO2 emission from the cement and concrete production. Now, right. I think with all the options we have, it's easy to get confused. What should we do, finally? And this is a question that will continue to be with us for the next 15, 20 years. Still, we need to act now. We need to start acting now. And that means we have to take whatever is available now and get going, and not forget about developing further solutions down the line, but we have to get going now. So I thought maybe the diagram, which I'm going to build up here, could help us get some orientation. This shows the several technologies which are available and which will be available in the future according to their technological readiness level on the x-axis, and on the y-axis, the cost impact of those. Now we know post-combustion carbon capture with amine scrubbing is available today. There are several pilot projects going on in the world. It is available, no problem, no doubt, but it is rather expensive, we know that there are cost optimizations possible by, for example, applying oxy-fuel technologies which concentrate the off-gas with a higher degree of CO2, which makes it easier to capture. We know about indirect calcination technologies like the Scarlix process LILAC, which is also being piloted these days. Also, this allows to extract a pure CO2 stream, which is only a partial stream. So this will also be bringing down the costs. And we know this calcium looping process. We have been listening to a presentation this morning that has given a good overview on this. But there are also other ways, and ways which are very mature already today and which are much more cost efficient. And first of all, to mention here, alternative fuels. And this is something, you know, in Europe, there is a high utilization rate already. The Indian industry has a huge potential in increasing the use of alternative fuels for reducing the fuel cost and the CO2 emission at the same time. Supplementary cementitious materials, of course, also very mature, can be used in specifically calcined clay. Is a huge topic that will be coming up unavoidably, and it's a good thing to go into that direction. Alternative raw materials, of course, also play a role. And RTOs, which means runtime optimizers, also increasing efficiency of the production of cement all the way through the value chain. Now, if we try to cluster this in terms of what is available now, we see that this first cluster is already available now, and there is no reason why we shouldn't act in introducing and implementing that as much as possible. Then the second cluster is available now, but very expensive, post-combustion CCUS. For my understanding, this is going to be a bridge technology and not sustainable. And then we finally have those future technologies which still need some piloting and developing. And there's a whole lot of technology development on the line. The community is very actively searching for that cluster that is being grouped as innovative technologies. Now, very briefly showing what is available now already in terms of alternative fuel. This is a picture of the so-called pyrorotor, which is a reactor system we have developed to utilize very coarse, unpreprocessed, humid material, ideal for utilization in the Indian cement industry. Long retention time, burnout without sacrificing the clinker quality, because it separates the combustion of the hard to ignite and how to burn out fuel from the clinkerization process. This is how it works. I think you've been seeing this flow sheet already. It's good for NOx reduction as well because it works on reducing atmosphere. Calcined clay, like other OEMs, KHD has developed calcined clay processes already back 40 years ago. Our first pilot installation with its flash tube calcination process. We can also convert rotary kilns to calcined clay. So whenever you feel like it, please approach us. We are sure we can handle and give you a solution for it. What we can also do, and I'm about to close, what we can also do for you is modifying your plant to satisfy requirements in terms of byproduct production. Like, for example, this is a technology we have developed for the processing of bottom ash. Bottom ashes, which are humid and containing oxidizable components, you can hardly use them. You have to pre-process them. And we are ready to introduce and to modify your plant to be able to use even somewhat exotic byproducts which are available abundantly and will reduce your CO2 footprint. Also, we have developed RTOs, runtime optimizers, utilizing artificial intelligence in a special way where we say artificial intelligence alone doesn't make it, because it is good to recognize any patterns, but if there's the black swan coming, then artificial intelligence will not detect it. Process expertise is necessary, so we've set up a system ready for introduction. And closing my speech today, I'd like to deliver some take-home messages to you. Decarbonization of cement is mandatory and it is very urgent, and there is no way around it. I'd like to invite everybody to rethink his business model and to change this challenge into an opportunity, like it was said in Dalmia. Very important. Think out of the box. Very soon, first movers will be rewarded. I've told yesterday already, in Europe, there's a price up to €1,000 being paid on the grey market for a ton of CO2 not emitted. First steps are not too costly. Alternative fuels, alternative raw materials, SCM, RTO, runtime optimizers are available today. Plant-specific solutions need to be developed because everything will be depending on logistics in the future. Are you available? Is certain feed material for you available? Are you far away from a pipeline? Are you far away from a chemical facility? It will be highly individual in the future. And cooperation between cement producers and OEMs, suppliers, need to be intensified. Thank you very much for your attention.
Thank you. So we are running few minutes delay, but still we can take few questions.
So I'm from Heidelberg Gulshan. Many of us, have, heard speakers talking about CCUS. We need to, this is the step which can bring a lot of change, and the low-hanging fruits are over. This is, what we are going to aim for. Now, capturing and then its utilization. So capturing is okay. I mean, some projects are undergoing at various levels, but we heard speakers talking about when we migrated from the traditional, construction to the use of cement. From the 1,000 years of life, now we are talking about less than 50 years of a building life on an average. Now, when we start using these, captured carbon into the construction practices, what is going to be the impact? Did somebody, did any study on that? When this is being added into various aggregates, and these aggregates come to concrete, or it's in the blending material, and that blending material is used finally into blended cement. So that's I mean, a view, if somebody has any view on that.
So maybe Mr. Ojha.
Yes. So any value-added material, when it is used in the concrete, any material. So first we evaluate what is impact, because we are designing the concrete or concrete structure on the basis of two parameters, strength and durability. Without durability, there is no sustainability. So we must evaluate. It should not be compromised with the mechanical properties, and it must be not compromised on the durability property. So when any kind of value-added material out of the mineral carbonation will come, and it will be available commercially, then it will be evaluated for the durability properties also along with the mechanical property, and then a specification will come, and only then we can say that with that technology, the adequate TRL level has been achieved for the commercialization purpose. So we will have to adopt all the processes to come to the conclusion that yes, with this technology, with this material, and this is the specification of that material, because consumer in the construction industry will evaluate your project based on some specification which will be provided by the standards, and that standards and the test method also. So we have a process to follow. Let us produce some component, some material which can be used in the construction industry, either through any route, and then it will go through the process of evaluation and finalization of a specification, and then it will be used in the construction industry. So this process, any material will have to. So if you have any additional query, you can ask.
Hello.
Until now.
Some material will be produced, and it will be produced continuously for a period. Then the second and third process will be evaluated. Just like composite cement, we can say, we got a code, but we could not produce systematically because we had not evaluated properly about the durability property, and that's why for the 5 years or 6 years we are hanging in a. Now it is being concluded at the BIS level. So not only this value-added product out of the mineral carbonation, even if the conventional clinker substitution, any material you are using as a substitute, then it may have, I am not saying it will have, it may have some impact on durability property that will have to be established in a laboratory experimentally. Then it will have to be concluded, and then it will go to the BIS level, the committee will discuss, and then it will come to the application standards like IS 456, or if you are producing aggregate, it will go to the IS 383, or any other cementitious material, it will go to the CD2/1, which is responsible for the making standards for cement. And then from there, the commercially you can produce regularly, and it can be used by the consumers in the market. So this is the process, either clinker substitution, or you are producing aggregate, or whatever other materials are.
What he raised the question is about when you are using carbonated aggregate, so what could be the consequences with the concrete? I think his question is very right, because corrosion is the major problem with the concrete, and that too with the carbonation, not the chloride. So question is that when you are using carbonated aggregate, whether it will have any impact on concrete. Yes, it is a very question being thrown in the world, and of course, before it goes to the field, all these studies are to be performed, but broadly from scientific perspective, to me it looks like that once you have sequestered carbon dioxide with calcium hydroxide as a calcite, CO2 itself will not come out. It looks like that. But yes, the pH of the concrete remains one of the question, because some of the studies have shown that pH may go lower down. So once the your concrete is not sufficiently passive, so it may have more chances for the corrosion to increase. Yes, these are the questions which are floating, but to me it looks like, as a scientist I can answer to this, that because you are making carbon dioxide into calcite, So concrete slightly may go, because this calcite has a pH around 9-10. So it depends all, because what kind of calcite you are forming when you are making mineral aggregate. I did not present, but one of my students will make a presentation during the afternoon, that we need to look into that at what pH we are forming the calcite, number one. And overall, even if pH is a function of power, hydrogen power. So concrete is somewhere around 12. So it may go down to maybe, let us say 11.5 or so, but your concrete will remain sufficiently passive to prevent the corrosion.
Actually,
so this is
there,
my
there
answer.
is a point. The pH of concrete per se is important. pH of aggregate is not important.
Yes.
So pH of aggregate, so from where we are getting the pH in the concrete system? We are getting from the concrete, the first dissolution of alkalis, and then after reactions, reserved alkalinity is calcium hydroxide. So pH we are not getting from the aggregate. So if you are producing aggregate and it has a lower pH, that will not affect the durability of concrete per se, reinforcement corrosion, which is primarily it is thought of carbonation-induced corrosion. So carbonation-induced corrosion, by manufacturing a aggregate having lower pH value, will not affect the durability of concrete as my scientific knowledge is concerned. But that will have to be established in the laboratory when you will be producing the aggregate. That was my point. Okay? So if you are producing a sequestered cementitious material altogether, then it can be. So that experiments will have to be conducted differently. So as I was explaining, that whatever you are producing, that will have to be experimented, and that will have to be established that it is having no impact on durability or marginal impact, for which a different mitigation strategy can be taken up. So having a complete information about any product, and then according to the information, if you are making the strategy to use it in construction, that will be the right step. Okay?
Thank you. Sir, may I? Actually, my question is with the scientist NCB.
I'm not from NCB.
Oh, sorry, NCB RI.
Okay.
Right. So, sir, it's a great achievement that we are thinking for the bricks manufacturing industry, and lots of initiative like utilization of low-grade fuel in the bricks manufacturing. But still, sir, it's a small-scale industry and a very poor control over the emission, like that, what they are producing. Can we not think about something changing small scale to medium or bigger one, and controlling the emission altogether? Also, it's a thought because when we are approaching to the city or outskirt area, there is a lot of pollution that is generated from these one, and at least bothered by any government authority or controlling authority. Thank you.
Yes. See, from cement industry, earlier the pollution level for suspended particulate matter was 750 microgram per meter cube. It has been now further strengthened by, now it is 250 microgram per meter cube. And the technology that I showed something, it can bring down less than 100. So the number one. And so now we are approaching Pollution Control Board also, that we can further strengthen down the pollution norms. That is one thing. Second thing, it's a rural-based technology. So any innovation that we have to bring, means any disruptive technology, if I try to think of, it will not be adopted in the field. So whatever we have to think of, slow. Construction industry is very orthodox. So any changes has to be very slow. So what we have proposed, that with your existing brick kilns, without changing anything, rather than putting external coal, you mix the coal. So what is to be size of the coal, how much the calorific value of the coal, and apart from reject coal, we can use agro waste also in that. And we have found, because cement industry 50% cost is the coal only. So if we can reduce the coals, it is a direct saving to the brick kiln owner. So it is an advantage to him. And when we are saying that pollution level is brought down less than 100 microgram per meter cube, this is an advantage to the society. Now the third things come, capital cost. Because we are going from mechanization, manual process to mechanization. So as you mentioned, are we not going? Yes. When we are going from manual to mechanization, his production level will increase. So again, he will have higher benefits into that. Actually, so all these advantages are there, but slowly. Yeah.
Mr. Singh and Anand, you can discuss afterwards also.
Yeah.
So we are running little short of time, and there is
Thank you,
need
sir.
to conclude now.
Yeah. Okay, we can.
Thank you, sir.
We can discuss over a cup of tea. Okay?
Right, sir.
So I must congratulate and compliment all the paper presenter in terms of presenting their different technologies or the concepts or the actual results related to carbon capture, utilization, and storage. And as you see, everyone is covering the entire value chain of the cement production, right from the use of renewable energy, especially a lot of changes required in the cement plant itself, utilization of AFR, energy efficiency, and all. So, more or less, all the session covered all aspects related to CCUS, and I must compliment NCCBM for bringing all these papers together. And there's a need. The CCUS, if you heard about the cement sector or a concrete, the first thing is asked is you are a hard-to-abate sector. So how you are taking care of CO2, and having this session specifically on the CCUS is most important. I must compliment all the presenters. They have presented with the facts and figures how much the CO2 they can reduce, and the industry also the case studies were excellent, and I compliment all, though we have to rate the presenters, so it's very difficult task for us, but I must congratulate and compliment all the presenters. Wish you all the best. Thank you.
So, thanks, Kaustubh. I would like to thank the NCCBM for arranging this technical session. Excellent and quite detailed presentation were made by well-known experts, researchers, and the leaders from industries. The key takeaways are excellent summary by Mr. Ojha on various measures for controlling the CO2 emissions and technologies which are available globally. Good presentation by FLS by process optimization, reducing the CO2. Valuable suggestion on the usage of XRF and XRD for reducing the CO2 by controlling and optimizing the raw mix. Speeding up thermal substitution rate by installing step combustor using the calcined clay and oxy-fuel development is surely going to benefited as presented by ThyssenKrupp. Future building materials technology as supported by CSIR would be the high benefit for reducing CO2. Its success may change the way we see the future for the cement industry. It's nice to see good effort by Dalmia Bharat Cement for reducing CO2 emission level and roadmap to achieving the net zero. Nice examples of new installation at Chettinad Cement by KHD. This shows how the OEM and plant can optimize the standard by adopting the new technologies. Extending the use of AF in captive power plant by Dalmia and achieving 25% substitution is commendable and appreciable. The new product pyro rotor as proposed by KHD would be, we believe, would be of great help in increasing the AF consumption in the coming year. At the end, once again, I thank all the presenters for their excellent work and for giving insight on reducing CO2 emissions.
Thank you.
Thanks.
Thank you very much, Chairman Sir and Co-Chairman Sir, for conducting this session so effectively. So now I request Shri Ojha Sir to present a memento to our Chairman and Co-Chairman Sir. Once again, thank you very much.